Electric potential energy is the energy that is needed to move a charge against an electric field. So if we have an electric field pointing, let's say, this way, this indicates that the electric field emerges from a positive charge into a negative charge. So if we have a charge Q and we want to move it against the electric field, we need energy. This energy is the electric potential energy. So this energy is used to move the particle away from the plate, and it is stored in the particle. So this energy is stored in the particle in the form of electrical potential energy, where the formula for electrical potential energy is where U is the potential energy is equal to Kc Q over R. So U is the source of U is the electric potential energy. It is measured in joules. Q is a charge in coulombs. Q is the other charge in coulombs. R is the distance from Q to Q in meters. This is an example. What is the electrical potential energy of a group of charges in the figure? So we have three charges. I will label this one with Q1, this one will be Q2, and this one will be Q3. So the potential energy is equal to the potential energy of 1, 2 plus the potential energy of 1, 3 plus the potential energy of 2, 3. So U is equal to Kc Q1 Q2 over R12 plus Kc Q1 Q3 over R13 plus Kc Q2 Q3 over R23. U is equal to, I will take Kc as a common factor, into Q1 Q2 over R12 plus Q1 Q3 over R13 plus Q2 Q3 over R23. So U is equal to Kc is 9 times 10 to the power of 9. Q1 is negative 1 nanocoulomb, so negative 1 times 10 to the power of negative 9 multiplied by Q2, which is 2 nanocoulombs, so 2 times 10 to the power of negative 9. The distance from 1 to 2, R12, is 3 centimeters, or when we convert it, it's 3 times 10 to the power of negative 2 meters, plus Q1 again is negative 1 times 10 to the power of negative 9. Q3 is negative 1 times 10 to the power of negative 9 over the distance from 1 to 3 is also 3 centimeters, so 3 times 10 to the power of negative 2 plus now Q2, which is 2 times 10 to the power of negative 3, negative 9, since it's in nanocoulombs, and the Q3 is negative 1 times 10 to the power of negative 9 over the distance, which is 3 times 10 to the power of negative 2. So the answer for you will be, negative 9 times 10 to the power of negative 7 joules. The unit for energy is joules. Electric potential is a location dependent, so it depends on the location. So it's a location dependent quantity that expresses the amount of potential energy per unit of a charge at a specific location. So electric potential depends on the position in the electric field. So if we consider a charge Q its potential at this point is different from its potential at this point is different from its potential at this point, depending on the distance. Let's assume this is R1, R2, and R3. It's the same charge, so the formula for electric potential which we will use will be V equals Kc Q over R. Since Kc is constant and it's the same charge, then we are talking about the position or the distance from the charge to the position in the electric field. We will see this in more details later in this video. So the electric potential by a mathematical representation is the potential energy divided by the amount of a charge. So it's U over Q. The electric potential is symbolized by V, where V is the electric potential measured in volts, and 1 volt is equivalent to 1 joule per coulomb. So both V, the electric potential, is written as V, and the unit, which is volts, is written as V. 1 volt is equal to 1 joule per coulomb, or the amount of potential energy per unit charge. And U is the potential energy measured in joules, and Q is the amount of charge measured in coulombs. So now we will use the same formula. Electric potential energy over amount of a charge gives the electric potential. So V equals U over Q. In the slide of electric potential energy, we said that U is equal to Kc Q1 Q2 or QQ over R. So I replaced the electric potential energy by its formula, the part in red. It's still over Q. So Q crosses out with Q, and we will get V is equal to Kc Q over R. This is how we derive the formula, where V is the electric potential measured in volts, U is the electrical potential energy measured in joules, Q is the amount of a charge in coulombs, and R is the distance, as you see, from the charge to where we want to find the electric potential. So it's from the center of the charge to the position in the electric field. We will solve an example now. Find the electric potential of a 5 nanocoulombs charge at a point 10 meters away from the charge. So we have the charge given as 5 nanocoulombs. We convert 5 times 10 to the power of negative 9 coulombs. And R is given as 10 meters. To find the electric potential, we will use the formula V equals Kc Q over R. So V is equal to, Kc is 9 times 10 to the power of 9. Q is 5 times 10 to the power of negative 9 over R, which is 10 meters. So we have 45 over 10, and V is equal to 4.5 volts. This is how we solve for electric potential. Another example, find the electric potential of a negative 4 microcoulomb charge at a point 3 meters away. So the charge is given as negative 4 microcoulombs times 10 to the power of negative 6. And the distance R is 3 meters. So we use the same formula, V equals Kc Q over R. Then V is equal to 9 times 10 to the power of 9. Q is negative 4 times 10 to the power of negative 6 over R, which is 3. So we have 12,000 volts. Negative. So as we saw from this example and the one before, when the charge is positive, it produces it has a positive electric potential, and when it's negative, it has a negative electric potential. The electric field always points out of a positive charge or diverges out of a positive charge or into a negative charge. So we take this as a reference for us. from where the arrow is emerging, we consider that we have a positive polarity, and where it converges in, we consider that it has a negative polarity. So when we have a positive side, this indicates a high electric potential, and when it's negative, it indicates a low electric potential. The electric potential is the scalar sum of all individual electric potentials of charges in the system. So in this system, if you wanted to find the net electric potential at point D, it is equal to the electric potential produced by A plus the electric potential produced by B plus the electric potential produced by C. So the electric potential will be, since the formula of the electric potential has Kc, so VA has Kc, VB has Kc, and VC has Kc. So I will take Kc as a common factor into Qa over Ra plus Qb over Rb plus Qc over Rc. So V is equal to Kc, which is 9 times 10 to the power of 9. Okay. Qa is given as negative 2 nanocoulomb, so it is negative 2 times 10 to the power of negative 9 over the distance from A to D. So it's this distance is the same as this distance, which is 4 meters, plus Qb, negative 6 times 10 to the power of negative 9 over the distance from B to D is an unknown. So if I consider this right-angled triangle, this one, this side is 4 meters, this side is 4 meters. So if I call this RB, then to find RB, I will say RB is equal to square root of 4 squared plus 4 squared, and this results in 4 radical 2 meters. So over 4 radical 2 plus Qc, which is 10 nanocoulombs, so 10 times 10 to the power of negative 9 over Rc, which is the distance from C to D, which is the same as 4 meters there, so over 4. V is equal to 2.5 times 10 to the power of negative 4 volts. This is V at point D. I found the net or the resultant electric potential at point D. Find the net electric potential at point D. So again, at point D, the distance from D to C is 4 meters, the same as this distance, and CB is the same as AD. So this will be also 4 meters. So V is equal to VA, so this is V at D, plus VB plus VC. So V at D is equal to Kc QA over RA plus QB over RB plus QC over RC. So V at point D is equal to 9 times 10 to the power of 9. QA is 9 nanocoulombs, so 9 times 10 to the power negative 9 over the distance from A to D is 4 meters, plus QB, negative 6 times 10 to the power of negative 9 over RB, which is this distance. Again, we find it using the Pythagorean, so RB is equal to square root of 4 squared plus 4 squared, so RB is equal to 4 radical 2 meters. So over 4 radical 2 plus QC, which is negative 10 nanocoulomb, so negative 10 times 10 to the power of negative 9, over the distance from C to D is 4 meters. So V at D is equal to, so the answer is negative 11.8 volts. So also for the net electric potential, it can be positive as in the previous exercise or negative as in this exercise. Find the net electric potential at point D, where D is given as a midpoint between A and B. So if the whole distance is 4, then this part will be 2 meters and this part will be 2 meters. Okay, so V at point D is equal to the potential of point A plus the potential of point B. So V at point D is equal to Kc into Qa over Ra plus Qb over Rb. Then V at point D is equal to 9 times 10 to the power of 9 into Qa is negative 9 nanocoulomb, so negative 9 times 10 to the power of negative 9 over the distance from A to D is 2 meters plus Qb, which is 9 times 10 to the power of negative 9 also over 2 meters, and V at point D is equal to 0 volts.